All right. So we're going to be doing things by hand for a little while. So let us say that you have a transfer function. Well, let me start from the yeah, we have a transfer function 2s plus 1 over s squared plus 4s plus 3, for example. Um, and we want to write the state space equation for it. We won't be going back through the thing about writing the state space equation for a differential equation um, to learn these signals. But what we want to do is just be able to look at this and write down the state space equation. So it's an S square, so that's the second order system. So that means that is a 2 by 2 matrix. So we're going to have 2 and we're writing this assuming that x1 is our, well, x1 gives us our y, or some form of our y, and x1 dot gives us x2 in some kind of way. So when we're writing this, we would write 0 and 1 as a standard. And for the denominator, we have 4 for the S and 3 for the, we would write -3 and -4. If we were multiplying these out, this would be -3x1, -4x2. x2 represents the derivative of x1. So the first derivative always goes with my x2, and the one that has no derivative always goes with my x1. That is how I remember it. 0, 1 is standard, and same thing again. So my output section, now my y for my output is going to be 2s. So I said the s represents the first derivative. So we're going to reverse the order again, 1 and 2, because remember now, 1 is going to go with the first derivative, and 2 is going to go. 1 is going to go with the output, 2 is going to go with the derivative of the output. So in other words, what I'm trying to say is this one is the s. x2 represents the derivative, which we call in the s. So that is how I remember to write them down. We're not so keen on writing it down
So
from
about the 3 out of the denominator. It look like a 2 right there.
which part?
Yeah, it just come back. It just come back.
Oh. All right. We're not so much worried about it in this strip here. MATLAB still loading back. So I don't know if anybody is tuned into MATLAB. I won't be able to use MATLAB for a while. It's just at 5%. So
I mean, you're just installing it, sir?
I don't know what happened to the computer. And in the middle of installing it, the computer locked down. And then, you know, that blue screen that you get where it's saying something went wrong
Yeah.
and lock off. Well, that's what happened after that. The second time in the middle of it. So I don't know. Anyhow, so we are going to, if we are using MATLAB, what we are going to ask you to do is the y is going to represent the denominator, the coefficients of the functions in the denominator. So the coefficients of your y in your denominator are 1, 4, and 3. And the coefficient of your x in your denominator is going to put 0, 2, and 1. And so you're going to write g is equal to transfer function x, y. And it will write it will supposed to write our equation as is here. So I don't know who have access to MATLAB. I'll give it, make you do the screen.
Yeah, write it in, sir.
We can share screen now.
Yeah, so allow that no security. Allow participants to share screen. Yeah. Oh. Oh. All right. So share the screen.
It's we cannot share it while somebody else is okay.
Yeah, so 0 to 1. Teach a high school picnic. Let's see if what them do we can do too. Right on the screen. Nope. All right. So that is going to write, like I said, it's going to write it back as a transfer function for you. So now, if you want to write it in state space, your square bracket to type it. Not k equal to, just square bracket. A, B, C, D, A, comma, B, comma, C, comma, D, comma. Sorry, take out the comma for the D. Square bracket, close, equal. Transfer function, TF, just TF. When you finish it, TF to T2, the number 2, SS, state space. open bracket, yeah, that one, x, y, x comma y. And press enter. All right, so you see, it has written the A, B, C. D is always there if the transfer function is not is one that is usable. If you get a value for D, then that transfer function is not a realizable transfer function. So it writes it for you, but notice that it's upside down, back to front. So it is x2, x1. The bracket is x2, x1. Right? So it's not x1, x2 like and you will see on the textbook, right? It is not x1, x2, it's x2, x1. It's upside down. So you see everything is back to front. And when you do the transfer function to state space for MATLAB. All right, so it's TF transfer function to state space. And you have it there. All right, so you're able to write the transfer function as in terms of state space easily. So now, if you are writing it with the x1, x2, just bear in mind that it is upside down. It is x2, then x1, not x1, then x2. All right. That is their software, and you can tell them how to write their thing. So that is just it. Like I said, every textbook will have it x1, then x2, but they have it the other way around. Now, there are some things that we need to be able to find. So, for example, is this system stable? Then we'd have to find the roots of the characteristic equation. So, so just type in like z equal roots. That was y.
Yo, scroll up your screen a little bit for please.
And there's a MATLAB have it, you know.
That's alright.
Yeah, close the bracket with the y, and so like z equal roots y. So you will get the roots of the characteristic equation there, or any equation. So it will tell you -3, -1, right? Or if you want the roots of the characteristic equation are the same thing as the eigenvalues of the matrix. So EIG of the matrix that you have common A. Supposed to give you the same 3, -3, -1. All right, so the roots of the characteristic equation and the eigenvalues of the matrix. And then you can look at that and say, what comment on the stability of the system and so forth and so on. So you can determine the stability. All right, you can just have about the screen a little bit. We need to talk about two other concepts before we go back. All right, so we need to talk about controllability. And observability. So let me put the definition. A system is controllable, and that is any system. any system at all, an economic system, electrical, mechanical, chemical, biological, and a biological system might mean the child that you had, the girlfriend or the boyfriend. I don't know if any girls in the class. So any system at all is controllable if and only if there exists, and that is the back way E means there exists. Get used to it.
Sir,
Mm-hmm.
you say Miss No one in that class?
Me say if I say if there, I don't know if any. That's why I say girlfriend or boyfriend.
Alright.
So it's controllable. If there's an input which we're going to call X that causes the output Y to go from its present value to a desired value in a finite time t. All right, um so let us say that this is your system and this is your present, and you want to get to over here, and so there must be an input u. All right, so the present X and Y. It doesn't matter how well, yeah, it doesn't matter as long as the time is finite. So you can't wait forever. So let me terrorize Zavina and say, let us say that the present state is girlfriend and the desired state is wife. Then the system is controllable. If you can, there's an input U that will take you from that state to the desired state. If there's no input, or if the input cannot take you there in a finite time, it's taking forever, then what we are saying is that that system is controllable. So the finite is important. All right, so the finite is important. This finite means unmeasurable. So finite also means measurable. So this definition controls talk about any system. So it is controllable. If and only if we have something where some input we can carry us from the present state to the desired state in a finite time. So if we can't find any input to carry us from, there's nothing that we can do to carry us to the desired behavior, then that system is uncontrollable. And if we can, if the input will get us there, but it's going to take not a measurable time. It's going to take till infinity for it to reach there. Then it don't make sense either because it will never end the same way. So by the time it reaches, so we still define it as uncontrollable. So That is the technical definition of something that is controllable. So, mathematically, we can determine that if we know the parameters of the system, we know the system matrix and all those type of things. So we can determine mathematically if a system is controllable. So what we'll do is form the matrix. And this is how the matrix, I'm going to call the matrix X. So it's going to be B, A squared B, A to the n minus 1 times B. Is full rank. So of course, when I was in math class, nobody ever explained to me what that means. A matrix with full rank. So let me, and so let me explain the rank of a matrix, and then explain the easy way to sort out this, and then we can look at 1 and 2 examples. So rough work aside, let us say I have this simultaneous equation. So this is my equation 1, and this is my equation 2. What can you say about these two equations?
One is half the other one.
One is half of the other one. So I multiply equation 1 by 2, and I get equation 2. So basically, it's only one equation that we have here. It's not two. They might try to disguise themselves as two equations because you see me write down two equations, but it's really one equation. Two of them is the same thing. So here is it. There's only one equation that we have here. So the rank of this set of equations is equal to 1. So if we have a 2 by 2 matrix, then to solve it, we need two different equations. So a 2 by 2, sorry, we have two set of variables, x and y. We need two equations to solve it. And that would mean if we have two different equations to solve it, then the rank is 2. So full rank means that the number of variables I have is the number of different equations that I have. So we can solve that. So we can solve that equation. Now, what that I will wait until you're doing your master's in control to get into all of that. But bear in mind that we have said that B is your input matrix. And we said that you must be able to find an input that way to take your system, which is A, from point X to point Y. So it must mean that when I take that system and put it together, I must be able to get a solution. So one of the things that we are looking at is that when you take the matrix and the system and put them together, we must be able to solve that equation because we are going to be looking for some x's and y's that will carry us to the point. Sorry, we're going to be still looking for a u that will carry us from point A to point B. The output that we want, y, is dependent on x1 and x2. So the system must be able to be solved. All right, like I said, I'll leave it for the when you're doing your master's and PhD, you know, control for them to go further. All I'm saying is that what we mean by full rank is that your system must be you must be able to solve the system. So the easy way to know if we can solve the system is that if you look at this set of equation, there's no one value that we're going to solve it. This has several solutions. So this is not a solvable system, but then what we can look at is the fact that the determinant which is 3 times 8 minus 6 times 4. 24 minus 24 is 0. So we can easily say that our system here is controllable if the matrix. So we can say the system is controllable if the determinant of x is not equal to 0. If the determinant is equal to 0, we can solve the system. So that is one way of determining it. Of course, so let us look at the example that we have here. The example that we are, let's do an example. Let me do an example. So we want to find out if this system is controllable. So now, we're going to form the matrix X, which is, well, let me write down first of all, what is A and what is B. So A is 0, 1, 2, 4. And B is the input matrix, which is 1, 2. So our matrix X is equal to B and then AB. It's a 2 by 2 matrix, so we're stopping at the second iteration. So if you know, if it's a 3 by 3 matrix, then we'll stop at the third iteration. That would be A, B, A squared B, and so forth and so on. So we can determine when to stop by the size of the system. So what we have up here is that we say we go B, A, B, A squared B down to A to the n minus 1B, because if it's a 10 by 10 matrix, then we need to have 10 terms inside that expression bracket there. All right. So our X is equal to B and then AB. So that is going to be X is equal to, like I said, I'm doing it by hand. So this is 1, 2, and then it's going to be 0, 1, 2, 4 times 1, 2 is equal to 1, 2. And if I multiply this matrix, that's 0 times 1 is 1 plus 1 times 2. You hear me just say 0 times 1 is 1. All right. So let's try that again. 0 times 1 is 0 plus 1 times 2 is 2. So that's 2. And then 2 times 1, 2 times 2.
In.
10. Yeah.
Yeah.
I just realized I said 2 times 1 and 2 times 2. It's 2 times 1 and 4 times 2.
Yeah, 10.
Which is 10. And the determinant of X is going to be equal to 1 times 10 minus 2 times 2 is 6. That's not 0. So therefore, the system is observable. All right. So what we are saying now is that whenever we're sorting out any system, when we're working out whether a system, any system at all, once we get the transfer function, one of the things the first thing that we must find out is if it is controllable. All right. Can't to you this year, but we would emphasize it in previous years. So if you go in the exam and you're asked to solve a system, you don't just jump and solve it, find out if it is controllable first. Because you will work and work and work and work and work and not get an answer. And you wonder, what we do wrong? We never multiply this right, we never do this. Some systems are not controllable. Just like some people. Just like some people are systems, can be viewed as systems. Some systems are just not controllable.
Sir, the statement, should that be observable or controllable?
Or controllable. When I reach observable yet.
Sir, next question, sir. It says 0 times 1 is 1.
Is 0.
So you're right back 1. Yeah.
Well, 1 times.
No man, you 1 and 2 depend that the side there before.
This 1 and 2 here.
Yeah, you just write them back.
Oh, okay.
Oh, should I put a bracket around this? All right. So system is controllable. So we can find an input to control the system to carry to the desired output. So all the things that you see I was doing before with the pole placement, we just need to be cognizant of the fact that going forward, whenever we have a system, we have to check if it is controllable, if there exists a solution for the system that we are talking about. All right, and if because if the system is not controllable, then we are going to be in a position where, like I said, we're going to be working towards a result, and we can reach it. And there are many systems that are not controllable. But most of the times we can use common sense and look and see that the system is not controllable. If I might get into politics, or not so much politics, but if you're going from the earth to the moon, so your present state is earth, and your desired state is moon. Can you find the input, which is the amount of gas or fuel that you would need to take you from here to there? And how are you going to get that fuel? You're going to need some form of propulsion, and you're going to need something to take you from here to there. And if you do your calculations, you will see maybe that something not right in the calculation. When I say something not right in the calculation, people have said that the moon landing is fake. The Americans were just trying to make sure so them outdo the Russians. So them stage this thing so they land on the moon and all of those type of things. But you can calculate and find out that but this thing is not, this thing requires an input where we cannot come up with at this present moment in time. But anyway, let me leave that alone. The times we are in, we need to be careful what we are talking about. Uncle Sam is listening. And others. All right. So let me stop share, and so we're going to take another system. So we're going to take another system, and we are going to find out if that system is controllable, but we're going to use MATLAB and do it. So ask Mr. Campbell to go back on MATLAB. And so we're going to type in the matrix A, which is 010 semicolon. Oh, put space between them for me. And then it's 001. And then it is -2, -3, -5. Yeah, can't close the bracket. So that is A. B now. What was B? Maybe
Be a 112.
B is 112. And but you have to put the out on the outside of the bracket. You have to put a transpose, which is the not the comma, the for the one code name apostrophe. We put the apostrophe at the end of that. All right, maybe see. All right, and then now, so we're going to say X is equal to open bracket B and then space.
Are that the bracket there, sir?
Yeah, same one. Space AB, A star B, space A squared star B, close the bracket. And then find the determinant DT X minus 226. So that's not 0. So it is not, it is controllable. All right. So I don't remember the command. CNT. Type in help controllable.
What that, sir?
Help controllable.
Oh.
We said that, come on, not last week.
I want L or 2
A
L.
12 in a controllable. I think. All right. Everybody, all right. Give me everybody. Let me just talk about observable, and then I'll give you the command because you never have to do all of that. That will do. You could just type in the command for controllable. And then from there you could take it. Yeah, my MATLAB is at 34%. All right. So I was looking at the command for controllable. CTRB. So to go back and go back to CTRB, open bracket, A, comma, B, and close the bracket. Okay, so I thought it was going to give you the determinant of the matrix. All right, now, so one other thing now. So type in rank, R-A-N-K, of the answer that you get. So rank answer. Supposed to get 3. All right. So rank supposed to give you 3. So if you type in rank and you can instead of typing in determinant, you can also type in the rank of the matrix, and the rank is a 3 by 3 matrix, so the rank supposed to be 3. That is full rank. So therefore, you have 3 distinct equations, so you can solve it for x1, x2, and x3. So you can also do that. Especially when you have a big matrix working with. I've seen people working with 200 by 200, sorry, 201 by 201 matrix. So you don't really want to go do A squared, B, A, and so forth, going down the line. So you just write controllable AB and then find the rank of that matrix. All right. So if you have a controllability, you can either put it out as we have it, or use the commands that we have here. All right. So let's go back and talk about observability. So a system is observable if the states So our system is observable if the states of the system, so x1, x2, x, whatever the states are of the system, you can calculate or measure them at any given time t. You can calculate or measure them at any given time t. So let us give a practical example. This is a furnace, and it is operating at 3000 degrees. Any sensor you put inside here, So any sensor that you put inside here is going to melt. So you can determine the temperature. And if you can determine the temperature, which is one state of the system, maybe if I'm assuming say it's a furnace, so one of the states of the system that you want to know is what the temperature is. So if you don't know the temperature, then you can't control the temperature because you don't know it. You can't determine it because there's no way you can use to measure it. All right. Of course, that leads to this thing here that them having control called state observer. So if you put the sensor out here, so and take the temperature out here, so you can calculate what you think the temperature inside the furnace is going to be. So in this case here now, the sensor would be called a state observer. So so you can use this now, the sensor over here, to estimate what is the temperature inside the furnace is going to be. But this is one system in which, like I said, if you cannot observe a state, if you cannot measure a state, so let me put measure up here because we are talking about measurement. If you cannot measure a state, then you cannot make your calculations because your output is going to be dependent on your states. This is that the y is equal to something times x1 plus something times x2 plus something times x3. And if you don't know what x3 is or x2 is or x1 is, then you can't calculate your y. So sorry, this is not a state observer. This is a partial state observer. So observability is also key in our calculations for controlling a system. Now, mathematically, now, if you recall, C is your output matrix. C is your output matrix. So if C is your output matrix, then what we are saying is that your output times your system, when you put them together, you're supposed to get a solution for each of the x1, x2, x3, x4, x5, and so forth that are in your system. So you can calculate the value for each state. All right. So like I said, leaving it there when you do your master's in control in Europe. And by the way, the Center for Studying Control is not the USA, it's Europe. So let's go again. So we want to find out if this system is observable. Me a second there. Thing up here so it's making one whole heap of nice. No switch data available. All right. So now, so we want y, which is c and c times a, which is going to be equal to -3, -1, and then -3, -1. Somebody at the door, so come back again. All right. So okay, so we have C times A, and our A is 0, 1, 4, 3. So we're going to, oh, ah, maybe that is why. So I'm plugging in the computer. All right. So that's -3, -1, and 3 times 0, 1, -1 times 4. That is -4. And then 3 times 1. I mean, 3 times 1, -1 times 3. -3 times 1, -3, -1 times 3, that's -6. That's what my y is equal to. So the determinant for y is going to be equal to -3 times -6 minus -4 times -1. We know that that is 18 minus 4 equal 4, not equal to 0. So the system is observable. Means that we can know all the states at all the times. We can stick in a meter, try to do some calculation, and find the value for each of the states at all different times. So the thing about it is that yes, I'm working out the nice clean examples in class, but when you have the systems in real life, it's a whole heap of zeros. Like I said, the last one that was kind of helping with was a 201 by 201 matrix. So before you do anything with it, you have to find out if it is observable or controllable. And yes.
Sir, the matrix on the row, sir. Oh, that was, sir. Come in, understand. Oh, you're right, sir.
Oh, so this is C, which is -3, -1, and then is CA, which is -3, -1. So it's going to end up giving you a row 0, 1, 4, 3. So that's what I was taking. First one is the first row, 3 times 0, 1 times 4, -1 times 4. So that would be 3 times 0 plus -1 times 4. And that is your first row, which gives me the -4. And then the next one is 3 times 1, -1 times 3. So the next row is -3 times 1 plus -1 times 3. So the first one in red give me the first, the -4, and the one in blue give me the -6. Alright. But you never fret up yourself too much about the multiplying of the matrix because let us see how far I got so that I can declare independence from the CC one. Nope, can't declare independence. So bigger matrix. Alright, so we want to determine if that matrix is observable. Alright, so let me hand back over to MATLAB. So now our matrix A is 0, 0, 0, 1, 0, 0. 0, 0, 1, 0. 0, 0, 0, 1. -4, -6, -2, -1. B is equal to 0, 0, 0, 1. And we have to put a bracket, apostrophe, and C is equal to 1, -5, -2, -4. That's our C. And then our Y now, Y equal C
How that go, sir?
C, Y equal square bracket C. Then the next one is C times A. Then the next one is C squared times A. 4 of them we must have. And next one is C cubed times A. Close bracket. apostrophe for the transpose. Oh, sorry, wrong. So put what is C times A squared and C times A cubed. Oh, next thing. Put in put it back and put in a semicolon in between each of the terms. Okay. And then you can type in rank Y or determinant of Y, whichever one. The rank of Y is 4. Determinant of Y not equal to 0. Then it is all right. So now the two things that you have to determine before you launch off onto any of the things that we have been talking about is that you have to to you have to determine whether they're observable and controllable. Because if they're not controllable, you can't find an input, and if they're not observable, you cannot find a state. Or one or two of the states cannot be determined. All right, now observable. OB Olux. SR SV. Type in OBSV. Teacher should no, just type in OB. Wait. Bring back. OBS. Just type in OBS. And then type in A bracket A and C and save. Okay, so it asks me, right? Is that the same matrix? This one is transpose. All right, the one is a transpose of the other. It doesn't really matter because whether the transpose are the right way. You still can determine. So it's OBSV. I was correct the first time. All people can remember the command in them head here. All right. So now you can get the observability matrix, and then what you do is that you would find the determinant or the rank of the observability matrix, and then that would tell you whether the system is observable or not. All right. So there we go back now and look at our problem. and then discuss how it is that we would do the problem.
Sir, you can go back up to the question 1 second.
This question here are the one that we work out.
The answer, I got it. Thanks.
All right. All right, so we can attempt this problem here now.
Yes, sir.
May say yes or no.
Yes, sir.
Okay. So the first thing we have to do is go through this same thing that we talked about last week. I just checking. Something here. Okay. So so um so once again we have to find damping ratio. So that is how much that work out to? ln squared 0.1 over pi squared plus ln squared 0.1. How much that work out to? I think we work it out already. Yeah, how much you get for this?
0.69.
0 point?
No, it's wrong answers.
What you get? That. What did I get? I don't have a calculator with me, so what you can use. Yeah, nobody now talk to me, so we get 0.349. That is what we're working with. Are you still there?
Yes, sir, we're still here. A bit distracted. Yes, sir, we're still here. A bit distracted.
Okay. So all 22 are still distracted. Sorry, all 21. All right, circle
Sir,
time.
now 0.591.
Right.
Yeah, man. No, we get a volley the 2 time already.
Yeah, exactly. All right. What's the formula for cycling time?
We got 4 over whatever, something there again. Damping frequency, omega n.
So it implies that omega n is equal to 4 over
Damping frequency times cycling time.
times cycling time. 4 over 0.591 times. What we said the cycling time was again?
5 seconds.
5 seconds.
One 1.35.
0.35.
1.35.
So our GS, which is equal to omega n over s squared plus 2 damping ratio omega ns plus omega n squared, is going to be equal to 1.35 over s squared plus 2 times 0.591 times omega n, which is 1.35 s plus 1.35 squared. That's 2 times 0.591. 1.35.
1.59.
Got it, 1.6.
Point 82.
Alright, so 1.82. All right. So he's way doing that because we're going on MATLAB after this. So our equation is 0, 1, 0, 0, 0, 1, negative 2, negative 3, negative 5, 0, 0, 1, and this is 0, 2, 1. All right. So So write down this equation for GS, and then we're going to MATLAB. All right, so Sir Campbell,
Yes, sir.
we're going to MATLAB now. All right, so we're going to, our transfer function is 1.35 divided by s squared plus 1.6 plus 1.82. So first thing we want to do is find the roots of the denominator. So we're going to type in x is equal to the 1 square bracket is a vector, right? 1.6, 1.82. Put in the 1.6.
What that, sir?
1.6, 1.82.
Oh, sorry. 6.82.
All right, close the bracket. And then we're going to set the roots of x. So we want to solve that equation for the roots of x. All right, so the roots of x, let me see, that is 0.8. 0.8. All right, so remember now, it's a 3 by 3 situation we have. So the new root that we're going to put in, the desired roots are 0.8, negative 0.8, negative 0.8. So we're going to put in another root. So the root that we're going to put in is going to be 10 times more than that. So it's going to be negative 8. So here's what I'm going to ask you to write down. Now, when we're doing the thing in MATLAB, we are going to write down the 3 roots. So we're going to write down K, capital K, is equal to the square bracket. So we're going to put in negative 8 and the other 2 roots that are there.
So that is negative 8, and then you have negative 0.8 plus 1.08. I can put in the I just like how
Yeah.
it is there. Right. Minus. Should I just copy this in?
Sir, where did it come from?
Where the 8 come from?
Yes, sir.
All right. Remember now, it's a 3 by 3 matrix we had. So we're going to put it's a second order system we just work out. So the 2 roots of the system are negative 0.8 plus or minus 1.0863i. So we have to put in a new pole in the system that does not affect anything. So that's why we said the new pole has to be at least 10 times the real part of the pole of the system that we, so that those two poles will be dominant and the other pole that we added is not
Oh,
dominant. So I just multiply the 0.8 by negative 0.8 by 10 and get 8. So I
oh,
put in that as the new pole.
okay, sir.
All right. So that is our the K represents the poles of the system that we now want. This is the design. So you can put a comment inside there. Say how you put comment in a MATLAB again. For that, oh, I'm gonna put the thing there. Percentage side.
You know, so I guess me not remember. You know, I think I
Take
this.
a percentage.
Oh, it's
Percentage,
percentage. Yes. Right.
All right. So desired poles of the new system. All right. So now, so this is the desired pose of the new system. So we're going to type in the old system now. So we're going to type in the A. So A was 0, 1, 0. Zero, zero, one, negative 2, negative 3, negative 5. Put in the space them.
Yeah, man, them in there.
0, 1, 0. All right. And then we put in our B. Zero, zero, one transpose. Come out outside. And put in our C. Which is 0, 2, 1. All right. Now, you're going to type in, so now, when we're using pole placement by this method, what we are going to say is place, what variable are we going to use? Z. Z equal place, Z we use it. I shouldn't have called the thing up here K. I should have called it P for poles, but all right, that's all right. So call Z equal place, open bracket, A, see the example there, A comma B comma, we use K, capital K, yeah. So that those values that you get there now are the gains for the system that you would need to work out. All right. So that will be the method by which you work out the gains for the system. That the required gains. So that I should have called what I call K should have been P for poles of the system. And what I call it Z should have been K just to represent gain because we usually use K, K1, K2, and K3 for gain. But here is the thing that we are going to work on another problem now. And we're going to work it out exactly as how we are required to work it out. So so let's go back to the drawing board. It's another problem. All right, so as you can see, it's the same. We will end up with the same characteristic equation, but so let us go back through. As a matter of fact, let me change something so that I don't want us to miss anything in the calculation. Yeah, all right. We're going through the full calculation. So, okay. So in this one, we know that the damping ratio is 0.591. And then now we have omega n is equal to 4 over the damping ratio times the cycling time. Is 4 over 0.591 times 2. How much that work out?
3.38. 3.38.
2.38. So now
3.38, sir. 3.38.
3.38. So our GS is equal to omega n s squared plus 2 omega n s plus omega n squared. So that is 3.38 over s squared plus 2 times 0.591 times 3.38 s plus omega n 3.38 squared.
S squared plus 4s plus 11.42.
All right. So we need to write down that 3.38 over s squared plus 4s plus 11.42. And our original system, we need A and B and C. So minus 4 minus 2 minus 1. We write down that as a 7 or a 1. It don't matter to me. Write it down as minus 7. And then 1, 1, 2, 1. And then 0, 1, 2, 3.
Sir, scroll up, look a bit. We can't see where you're at.
Not writing anything. Just write it down so that when we go to MATLAB, we know. All right, so we wanted the transfer function. So this is the transfer function that we wanted. And then we write it down this as our system equation. So we need those two things. So this is our desired transfer function. And this is the system that we want to put this desired transfer function on. All right, I would call this a cell. All right, so we're going to go to MATLAB.
Oh, hold on, sir.
All right, so the first thing we're going to do is type in the equation that we have, characteristic equation of the desired equation. So that is x equal, what was it? 1411.42. And then we're going to find the roots of x. Like this MATLAB, it asks the questions. The other one never asks you nothing.
A new version, sir. New
Yeah,
version.
man, the other one was very Jamaican. Sit down
I look fire.
and look fine. All right. So now, our roots, -2, -2. So we're going to put in the new roots going to be 2 times 10, which is 20. So we're going to put -20 and -21. So our new, so we're going to call our new K, we're going to call it K now. The gains that we want, desired gains for the system, going to be those two up there, and -20, and we're going to put -21. But we can make it anything that we want, but we're making it -20 and -21. Multiply the -2 by 10, and we get the, and then we put in those two that we have. All right. So now we're going to put in our A. A is equal to, why we keep on, I shouldn't call it K now, it should be P. But anyhow, you know, you understand what I'm saying. So A is 0, 1, 0, 0. Remember the space. Zero, zero, 1, 0. 0, 0, 0, 1. And then -4, -2, -1, -7. All right, our B is 1, 1, 2, 1. Put on the transpose. And our C was 0, 1, 2, 3. All right, so now the what we want to find again. So we're going to say, so let me just call it G for gains. G equal place, as the pole placement method that we're talking about. So A, B, and K. Even that, once upon a time, MATLAB never used to tell you anything. So those are the gains for the system that you would require. But before you did all of that, you have to type in CRL find out whether the system is controllable. CT, what was it? Give me a second there.
The CRT.
Hello,
Let me scroll
you
up.
still in class? So CTRB,
Mhm.
A and B. And then you find the rank of that or the determinant, whichever one your finger can reach the fastest. So therefore it's controllable. And then okay, the rank is 4 and the determinant. No, and the determinant of you see, you can't find the determinant of the answer. Gosh.
Oh, so I just give you a random number.
And then you have to type in the observability O B S V A and C. And find the rank of that. They're very suspicious of that 4.
Come on, me too, sir.
Couldn't ask find
Type in rank bracket O B S V A C. No. You put in CC, you know, AC.
Like if you were right, sir.
Yeah, I think you're missing a bracket. Oh, did you mean? Okay, so it's 4. Oh, it's supposed to be 4. Is the determinant me suspicious of? All right, so we should have done that before we proceed to work out the problem, because if we do that after, like, well, these problems here, like I said, so most of the matrices that if you are involved in this kind of thing, then most of the matrices will have a whole heap of zeros. So you have to determine whether the rank, if it is observable, if it's controllable, before you attempt to use MATLAB to work out anything with any kind of control. Because most of the systems that you would be working with, like I said, the whole heap of zeros them have in them. Oh, and the next thing that you would have to work out is the determinant of A. The matrix A. The reason why you'd want the determinant of the matrix A, you want to find out if the system as it is stable or unstable. Wait a little bit. How the determinant of A is 4.
Everything run off. Everything add up to 4. Oh, add up the 7.
Something wrong, but anyhow. All right, so we're going to stop here for this evening. So like I said, stop in here for this evening, and then so we're going to finish looking at some things with the system, and then we have 2 other things to look at concerning this whole systems and finding the systems whether them can not and controlling the system and finding the gains. So we have 2 more things that we need to look at. And then we start giving them the assignment. All right. So we stop in here this evening, unless there are questions.
Sir, you can share back your screen for a minute. I missed that
I do
question.
have my earplugs, so I'm not hearing the question. Go on again.
You can share back your screen for a minute, sir. I missed the question.
Oh,
The last part above this, sir. Yeah, look a bit above that, sir. Yeah, right there. All right, thank you, sir.
all right. So so next week we continue with our discussion.
All right, sir.